Let E and F be two real normed spaces. A map F from E to F is called an isometry if the norm of f of x minus f of y is equal to the norm of x minus y in their respective spaces for all x, y in E. And F is called affine if f of 1 minus t times a plus t times b is equal to 1 minus t times f of a plus t times f of b for all t in R, and a, b vectors in E. In other words, this equation means that f preserves any point on the line through A and B proportionally. I hope those two definitions are clear. Now, think about the following question. When is an isometry affine? It makes sense to ask this question because some of you may have already learned in the Euclidean geometry or linear algebra that an isometry has great rigidity, and intuitively it should preserve any point on the line through A and B proportionally because of the distance preserving property of the isometry. You should have that kind of intuition. So that is the situation for the Euclidean spaces. But here, we are asking something more general. We are asking something that could be on the infinite dimensional spaces. I should emphasize that the norm on E and F are not the same. So strictly speaking, I should put a subscript E here and subscript F here. But if the norms are well understood, I may omit those notations. Okay, now for normed linear spaces in general, when is an isometry affine? Perhaps the most well-known answer to this question is the famous Mazur-Ulam theorem. This is in the year 1932. The theorem states that every bijective isometry between two normed linear spaces must be affine. And it should be very easy for you to see from the functional analysis that an isometry is automatically injective, simply from the definition of norms. So, the theorem really says every surjective isometry is affine. But it doesn't hurt to add the bijectivity here. At this point, in case some of you might be interested, let me tell you that the bijectivity here really plays some role. Since not all isometries are affine. So let me give an example. of an isometry that is not affine. So let me write this down as a remark. Not all the isometries are affine. So for example, let's take E to be the real line equipped with the absolute value as its norm, as 0. And let F be the plane, the Euclidean plane, equipped with the maximum norm. So here this notation means if you have vector its infinity norm or maximum norm is equal to the maximal guy of its components. Now let phi from the real line to real line be a contraction. And by contraction, we mean for any S, T in R, we have the absolute value of phi of S minus phi of T is less than or equal to S minus T's absolute value. Take, for example, the phi of X equal to the absolute value of X. Then, by a well-known inequality, this is automatically true. And let F from E to F sending X to the vector X, comma phi of X. Then F is an isometry. As long as phi here is a contraction. Since f of x minus f of y taking the maximum norm is equal to, so by definition, f has two components, x minus y, comma, phi of x minus phi of y. And this maximum norm is simply equal to the absolute value of x minus y. But of course, for any contraction phi, f is not necessarily affine. And as a matter of fact, f is affine if and only if phi is affine. There are too many contractions that are not affine. For example, this one is. For example, for phi of x equal to x, f is not affine. Since f of 1 plus negative 1 minus 2, which is f of 0, is equal to 0, 0, the origin. But f of 1 plus f of negative 1 divided by 2 is equal to 0, 1. So f is not affine from the definition. And that finishes this remark. Not all the isometries are affine.